All right, today we're going to become molecular architects. We're cracking the code on one of the most fundamental reactions in all of organic chemistry, electrophilic substitution on a benzene ring. This is literally the instruction manual for how we modify one of the most stable and most important molecules out there.
Okay, so think about this. Benzene, with its perfect little ring of electrons, is notoriously stable. It's kind of happy, just the way it is. So that presents a really cool chemical puzzle, right? If it doesn't want to react, how in the world do we convince it to change so we can build bigger, more complex things? Well, that's exactly the puzzle we're going to solve.
So here's our game plan. First, we're going to break down the signature reaction itself. Then, we'll meet the cast of characters, the chemical attackers that get the job done. After that, we'll get into what happens when the ring isn't a blank slate, which is where it gets really fun. And finally, we'll look at the speed controllers that can either slam on the brakes or hit the gas on these reactions.
All right, let's start at the beginning. What is this reaction all about at its very core? If you take away only one thing today, let it be this. Seriously, electrophiles love electrons. The name literally means electron-loving. This simple idea is the master key. It's what unlocks everything else we are about to talk about.
So the official name is electrophilic aromatic substitution, and it's one of those great names in chemistry that tells you exactly what's happening. You have an electrophile, our electron-loving species, that shows up to an aromatic ring, like benzene, and it substitutes one of the hydrogen atoms. It just kicks a hydrogen out and takes its place. Notice it's a substitution, not an addition. That way, the super-stable aromatic ring gets to stay intact.
And this picture shows the whole dance perfectly. Over here, you've got the benzene ring, just loaded with that cloud of electrons. Then in comes the electrophile, shown as E+, and it is desperate for those electrons. So it attacks the ring, and in the shuffle, a hydrogen ion gets booted out. Simple, elegant, and incredibly powerful.
So we get the general idea, but who exactly are these so-called electrophiles? Let's meet the main players, the usual suspects that chemists use to get stuff done on a benzene ring.
Here are the big five. We can add a chlorine atom, that's chlorination. We can add a nitro group through nitration, and so on. Now pay special attention to those last two, the Friedel-Crafts reactions. They are a huge deal because they let us build new carbon-carbon bonds, which, is pretty much the whole point of organic chemistry.
Now here's where it gets clever. These attackers don't usually just hang around waiting. We have to make them. For nitration, you mix together concentrated nitric and sulfuric acids. That chemical reaction creates the real weapon, this superreactive nitronium ion, NO2+. That's the electrophile that actually goes and attacks the ring.
And it's a similar story for the Friedel-Crafts reactions. To get a carbon chain to attack the ring, you need to make it hungry for electrons. So you use a catalyst, like aluminum trichloride, to help create a carbocation. That's a carbon atom with a positive charge. And bam, you've got your electrophile, ready to go build a bigger molecule.
Okay, this is where it gets really interesting. So far, we've only been talking about a plain, naked benzene ring. But what happens if something is already attached to it? This is the plot twist.
See that group that's already on the ring? It's not just a spectator. It's active. It acts like a traffic cop or a gatekeeper. It has very strong opinions, and it tells the next incoming electrophile exactly where it can and cannot attach.
So how does it do that? Well, this directing power comes from something called the resonance effect, or R effect. And it's basically a tale of two types of groups. Some groups have what we call a plus R effect. They're generous. They donate or push their electron density into the ring. Then you have the others with a minus R effect. They're greedy. They pull electron density out of the ring. And you can see the result right here. Look at these diagrams. A plus R group pushes electrons in, and it specifically makes the spots right next door, the ortho positions, and the spot directly across, the para position, extra rich in electrons. But a minus R group does the opposite, pulling electrons away and making those exact same ortho and para spots electron poor.
So now we just go back to our golden rule. What do electrophiles love? Electrons. It's that simple. If a ring has a plus R group on it, the electrophile is going to be drawn to those super electron-rich ortho and para spots. But if the ring has a negative R group, the electrophile is actually repelled by those electron-poor ortho and para spots. So where does it go? It goes to the next best place, the more neutral meta position.
Okay, let's get to our last piece of the puzzle. These groups don't just direct traffic. They also control the speed limit for the entire reaction. They can act as an accelerator or as a brake.
Let's start with activating groups.
These are the electron donating groups, or EDGs. By pushing electrons into the ring, they make the whole thing more negative, and therefore way more attractive to an incoming electrophile. The result? The reaction speeds up. It's like putting out a giant flashing neon welcome mat.
And on the flip side, you have deactivating groups. These are the electron withdrawing groups, or EWGs. They pull electron density out of the ring, making it less electron-rich and, you guessed it, way less attractive to an electrophile. This slams on the brakes and slows the reaction way, way down.
Now, a group's identity as an activator or deactivator is ultimately decided by a chemical tug-of-war. There are two forces at play: the resonance effect, which we've already met, and something called the inductive effect, which is an electrical effect that works through the single bonds.
This chart really puts it all together for us. If both effects are donating, like with alkyl groups, you get a strong activator. Easy. If both effects are withdrawing, like a nitro group, you get a strong deactivator. Also easy. The tricky ones are where they compete. For groups like an alcohol or an amine, the donating resonance effect is stronger, so they end up being activators. But, and this is the classic exception you have to remember, for the halogens, the withdrawing inductive effect actually wins the tug-of-war, making them deactivators.
And this quote from the source material absolutely nails it. When it comes down to deciding where that new group is going to go, ortho, para, or meta, it is the resonance effect that calls the shots. It's the one that's responsible for placing those electron-rich and electron-poor spots around the ring.
All right, let's boil this all down. What are the big takeaways? 1. Benzene's go-to reaction is electrophilic substitution. 2. The driving force behind the whole thing is that one simple rule: electrophiles love electrons. 3. Any group already on the ring acts as a director, telling the next one where to go. And 4, those same groups are also speed controllers, either activating the ring to speed things up or deactivating it to slow them down.
And that leaves us with one final thought. Because this isn't just theory, right? This is the playbook for synthesis. Knowing these rules lets chemists plan out how to build incredibly complex molecules. So think about it. If you needed to add 2 different groups to a ring to make a specific product, in what order would you add them? Because the order you choose, that determines everything. Thanks for tuning in.